Welcome to the lesson on Battery Management System Balancing Function. In this lesson, we will focus on one of the key functions of the BMS, balancing. Let us look at our lesson objectives. By the end of this lesson, you will be able to explain the need for cell balancing in battery packs. Next, you will be able to differentiate between active and passive cell balancing methods. Then, you will be able to identify the key components used in active and passive balancing circuits. Following that, you will be able to describe how the BMS monitors and manages cell imbalances. Finally, you will be able to list the advantages and disadvantages of active and passive balancing. The BMS plays a crucial role in maintaining the health and performance of a battery pack by ensuring that all cells within the pack are at balanced charge levels. This balancing is necessary to maximize the efficiency, capacity, and lifespan of the battery. Balancing can be achieved by the process of active and passive balancing. Active balancing involves redistributing energy among the cells to equalize their charge levels. Passive balancing involves dissipating excess energy from overcharged cells as heat. As we proceed, we will look at active and passive cell balancing in detail. Active cell balancing is a sophisticated method used in the BMS to ensure that all cells within a battery pack maintain an equal state of charge, SOC. This technique enhances the overall performance and lifespan of the battery pack. Instead of dissipating excess energy as heat, active cell balancing transfers energy from overcharged cells to undercharged cells. Active cell balancing method improves efficiency. This method is generally more efficient than passive balancing as it avoids energy loss due to heat dissipation. The image depicts the process of cell balancing in a battery pack. The image starts with 3 battery cells, each representing a unit within a battery pack. The cells have different SOC, with cell 1 being fully charged, 100%, cell 2 being partially charged, 50%, and cell 3 being discharged, 0%. A red arrow connects cell 1 to cell 3, indicating that energy is being transferred from the fully charged cell 1 to the discharged cell 3. This transfer is likely facilitated by a balancing circuit within the BMS. The image then shows the balanced state, where all 3 cells have a similar SOC, represented by the same level of green in each cell. This indicates that the balancing process has successfully equalized the charge levels among the cells. This image illustrates how a BMS can actively manage the energy distribution within a battery pack to ensure that all cells have a balanced state of charge, which is essential for optimal performance, safety, and longevity of the battery. Active cell balancing works by monitoring cell status, identifying imbalances, and actively transferring energy. Monitoring cell status. The BMS continuously monitors the voltage and SOC of each individual cell in the battery pack. Identifying imbalances. Cells with higher voltage, indicating a higher SOC, and cells with lower voltage, indicating a lower SOC, are identified. Actively transferring energy. The BMS actively transfers energy from the overcharged cells to the undercharged cells using various techniques such as inductors, capacitors, or direct energy transfer circuits. By actively redistributing energy, the BMS can effectively equalize the SOC among all cells in the battery pack, improving the overall efficiency and performance of the battery. The main components involved in active cell balancing are inductors or capacitors, switching devices, monitoring circuitry, and control logic. Let us look at them in detail. Inductors or capacitors are passive components that can be used to temporarily store and transfer energy between cells. Inductors store energy in a magnetic field, while capacitors store energy in an electric field. By using these components, the BMS can effectively transfer energy from overcharged cells to undercharged cells. Switching devices. Transistors or metal oxide semiconductor field effect transistors, MOSFETs, are used to control the flow of energy between cells. These devices can be activated to connect the appropriate inductors or capacitors to the overcharged and undercharged cells, allowing for the transfer of energy. Monitoring circuitry. This circuitry is responsible for continuously measuring the voltage and SOC of each cell in the battery pack. It compares the cell voltages and SOCs to determine which cells need balancing and the amount of energy that needs to be transferred. Control logic, read-only memory, ROM, random access memory, RAM. This is part of the BMS firmware that contains the software instructions for controlling the balancing process. It analyzes the data from the monitoring circuitry to decide when and how to transfer energy between cells, activating the appropriate switching devices and controlling the inductors or capacitors. The different methods used for active cell balancing are capacitor-based balancing, inductor-based balancing, transformer-based balancing, and direct energy transfer. Capacitor-based balancing uses capacitors as temporary energy storage devices. Capacitors are connected to high voltage and low voltage cells to transfer charge. Inductor-based balancing uses inductors to store and transfer energy. An inductor is charged by an overcharged cell and then discharged to an undercharged cell. Transformer-based balancing uses transformers to transfer energy between cells or groups of cells. They are often used in larger battery packs. Direct energy transfer involves direct connections between cells through switching circuits. Direct energy transfer allows for direct energy transfer from higher voltage cells to lower voltage cells. Let us look at the advantages and disadvantages of active cell balancing. Starting with the advantages, they are efficiency, improved performance, extended lifespan, and thermal management. Efficiency. Active cell balancing reduces energy loss by redistributing energy between cells rather than dissipating it as heat. This improves the overall efficiency of the battery pack, which is crucial to maximize range and reduce charging frequency. Improved performance. Active cell balancing maximizes the usable capacity of the battery pack by ensuring all cells are at similar SOC levels, which allows the vehicle to use more of the stored energy effectively. Extended lifespan. Active cell balancing helps to maintain balanced SOC across all cells, reducing the risk of overcharging or deep discharging individual cells, which can degrade them. This extends the overall life of the battery pack. Thermal management. Active cell balancing generates less heat compared to passive balancing, which minimizes thermal management challenges. Less heat production reduces the need for extensive cooling systems, saving space and cost. Now let us look at the disadvantages of active cell balancing. They are complexity, cost, size, and potential for increased conversion losses. Complexity. Active cell balancing requires more complex circuitry and control algorithms compared to passive balancing. The need for real-time monitoring and precise control increases the design and development complexity. Cost. More components, like capacitors, inductors, and control circuitry, and a sophisticated design make active balancing more expensive. This cost increase may affect the overall price of the vehicle. Size. Additional components required for active balancing can increase the size of the BMS, which may pose packaging challenges in compact spaces within the vehicle. Potential for increased energy conversion losses. Although active balancing is more efficient than passive balancing, some energy is still lost during the transfer process. These conversion losses can reduce the overall efficiency of the system, particularly if not optimized properly. Let us now look at passive cell balancing. Passive cell balancing involves dissipating excess energy from overcharged cells as heat. This can be achieved through various methods, such as using resistors or diodes. While passive balancing is relatively simple, it can be inefficient and can lead to energy loss. The BMS continuously monitors the voltage of each individual cell in the battery pack. The BMS identifies overcharged cells, meaning cells with higher voltage, indicating a higher state of charge. The BMS dissipates excess energy. Excess energy from overcharged cells is dissipated by bypassing current through a resistor connected across the cell. This process converts electrical energy into heat. By reducing the charge of the overcharged cells, the BMS gradually brings all cells to a similar voltage level, ensuring that the entire battery pack is balanced. The image depicts the process of passive cell balancing in a battery pack. The image starts with 3 battery cells, each representing a unit within a battery pack. The cells have different SOC, with cell 1 being fully charged, 100%, cell 2 being partially charged, 50%, and cell 3 being discharged, 0%. Resistive loads are shown above cells 1 and 3, representing the dissipation of excess energy. The resistive loads above cell 1 indicate that energy is being drained from the cell, while the resistive loads above cell 3 suggest that energy is being added to this cell. This process is likely achieved by using resistors or other means to shunt excess current away from the overcharged cell, cell 1, and dissipate it as heat. The image then shows the balanced state, where all 3 cells have a similar SOC, represented by the same level of green in each cell. This indicates that the balancing process has successfully equalized the charge levels among the cells by draining energy from the overcharged cell and adding it to the undercharged cell. The image illustrates how passive cell balancing works by dissipating excess energy from overcharged cells to balance the SOC among all cells in a battery pack. The main components involved in passive cell balancing are resistors, switching devices, monitoring circuitry, and control logic. Let us look at them in detail. Resistors are essential for dissipating the excess energy from overcharged cells. The value of the resistor determines the rate at which energy is dissipated. Switching devices. Transistors or metal oxide semiconductor field effect transistors, abbreviated as MOSFETs, are used to control the connection of resistors across the cells. When balancing is needed, these devices are activated to connect the resistor to the overcharged cell. Monitoring circuitry. This circuitry continuously measures the voltage of each cell in the battery pack. When it detects a voltage imbalance, it signals the control logic to initiate balancing. Control logic read-only memory, abbreviated as ROM, random access memory, abbreviated as RAM. Control logic is part of the BMS firmware that determines which cells need balancing and activates the appropriate resistors. It uses algorithms to analyze the cell voltages and decide on the necessary balancing actions. Let us look at the advantages and disadvantages of passive cell balancing. Starting with the advantages of passive cell balancing, they are simplicity, cost-effective, and reliability. Simplicity. The design of passive cell balancing is straightforward, requiring only basic components such as resistors, switches, and simple control logic. This makes it easy to implement and integrate into a BMS. Fewer parts mean less complexity, reducing the chances of design errors. Cost-effective. Passive cell balancing is less expensive because it requires fewer components, like resistors, and doesn't need complex circuitry or algorithms. This helps keep production and maintenance costs low. Reliability. With fewer components and a simpler design, passive cell balancing systems are less prone to failure. There are fewer parts that can malfunction, making the system more reliable and easier to maintain over time. Now, let us look at the disadvantages of passive cell balancing. They are energy loss, heat management, and balancing speed. Energy loss. Passive balancing dissipates excess energy as heat rather than redistributing it to other cells. This leads to energy wastage, reducing the battery's overall efficiency. For example, if one cell has a higher charge, the extra energy is lost rather than being used, affecting the battery pack's performance. Heat management. Because passive balancing generates heat as it dissipates excess energy, managing this heat is critical, especially in large battery packs. Inadequate heat management can lead to overheating, which can damage cells and reduce the battery pack's lifespan. Balancing speed. Passive balancing is slower than active balancing methods. This is because it relies on discharging the excess energy as heat, which takes more time. In scenarios where cells need to be balanced quickly, passive balancing may not be the most effective solution. According to the balancing principle, different currents flow through cells based on their SOC to achieve a balanced state. Why is balancing needed? Balancing is needed to prevent individual cells from overheating and failing prematurely in a battery pack. In passive cell balancing, the passive circuits dissipate excess energy from fully charged cells as heat, preventing overcharge. In active cell balancing, the BMS actively transfers a small amount of charge between cells, high to low, during charging or discharging to equalize the SOC. Effective cell balancing relies on accurately determining the SOC of each individual cell in the series. This allows the BMS to identify which cells need more charge or less charge and adjust currents accordingly. Let us now look at the lesson summary on BMS balancing function. Cell balancing is essential to ensure uniform charge levels across all cells in a battery pack, which improves efficiency, safety, and lifespan. Active balancing transfers energy from overcharged cells to undercharged ones, using components like inductors and capacitors to minimize energy loss. Passive balancing equalizes cell charge by dissipating excess energy from overcharged cells as heat through resistors. Key components such as resistors, metal oxide semiconductor field effect transistors, monitoring circuits, and control logic enable the BMS to detect imbalances and perform balancing operations. Active balancing offers higher efficiency and better performance, while passive balancing is simpler and more cost-effective but less energy efficient. Thank you.